Your friend traveling on a car from Sydney to his house in Perth. He will be traveling at 100 km/h speed, and the distance is 4,000 kilometer, and it would obviously take 40 hours for him to go to Perth from Sydney. And you are here in your little place, and you're able to communicate with your friend here. So your friend is sitting in the car, and you're here, and you're going there. So you both agree on the distance he's going to travel and the speed and the time it's going to take. So you both agree. So the distance is 1 kilometer. That is the distance, and it's going to take 40 hours, and the speed is 100 kilometer per hour. So we are assuming that there are no stopping places. He's just going straight to Perth. So this is for standard speeds like 100, 200, 1000 kilometer per hour. It's not a very high speed. So in that case, you both agree on the time and distance and the speed at which he was traveling. Now, let's consider another scenario. Your friend is actually now in a spaceship, and that's your little friend. And he is going to go to Mars. So, the distance of Mars from Earth is about 54 million kilometers. That's the distance can change, but the shortest distance is 54 billion when Mars is close to Earth. So you both agree on the distance. And now he's going at a speed of 0.866 of c. That means that it's 0.866 of the speed of light. So you have to multiply the speed of light, which is 3 times 10 to the power 8 meter per second, by 0.866. So he's traveling at that speed. And that's the distance. You both agree at the beginning Mars is 54 million kilometers away. So now here's the problem. So your friend went to Mars. So now his temperature and everything changed. He's different now. And you're communicating with your friend. So your friend is telling you, because obviously it's a 54 million kilometer, right? So 54 million kilometer, if you travel at 0.866 the c, it would take about 208 seconds. So according to you, it's 54 million kilometer, right? And the speed is 0.86 c, and the time is 208 seconds. So that you basically divide the distance by the speed, and you will get the time it takes. Your friend has reached Mars, and he's telling you a different story. He's saying that the Mars is only about 27 million kilometer, and he traveled at 0.866 c, the speed of light, multiplied by 0.88 c. Then he's saying that it took only about 104 seconds. So here's the problem. So you both agree on the speed at which he traveled, but you disagree on the distance. Although initially he told you that it's 54 million kilometer, now he's saying he traveled only about 27 million kilometer, and the time. According to your calculation, it took 208 seconds, but he's saying it took only 104 seconds. So this is he's telling the truth, and you are telling the truth, but he's values are completely different. So what's happening? His length. So the length he's talking about is the distance he traveled. We say is a length contraction. In terms of time, he's saying 104 and you're saying 208. So we call it time dilation. Einstein did lots of thought experiments because these type of things you can't experiment because we can't achieve that type of speed practically. But he came up with the theory, and that is for time dilation and length contraction. So he said that when the objects travel at relativistic speeds about, say, for instance, more than 1/10 of the speed of light, time slows down for the moving objects. Time contracts. So at the same time, an observer outside, the time dilates. It's a bit like you're sitting in the car park and your mother went to the supermarket, right? And your mother was there only for half an hour. So, but you say to your mother, You've been there for ages. You have been there for 2 hours, but your mother says, no, it's only half an hour. So basically, for you, the time dilated. But for your mother, time is running slow. But that is a kind of a psychology. That's not physics. But this is physics where things are real. That moving objects, if they are moving at a relativistic speeds, time slows down. So you and your friend agreed on the speed at which the spacecraft was traveling to Mars. That's V. And T0 is a time measured by your friend from his reference plane. So we call that as perfect time. So perfect time is the time measured by an observer from the moving plane about that event. Event starts from here and ends here, and that was measured by an observer in the moving frame. And you are a stationary observer in a stationary frame, and you measure the time TV. And we call this a dilated time because your time, according to you, it took longer. Regarding the distance, you know the proper length. The proper length is the exact distance from here to Mars. But your friend, according to him, it took shorter. It took shorter, and the distance is smaller than actual distance. So, according to Einstein, so he came up with this formula, a factor. That means, according to him, TV, which is the time that you are looking at, is equal to gamma time T0. So gamma must be greater than 1, right? Because TV is greater than T0, so gamma is greater than 1. So gamma, from his thought experiments, he derived a formula that gamma is equal to 1 over square root of 1 minus v squared over c squared. So here v is the speed of the spacecraft and c is speed of light, and you have to get the square root, and 1 over that is gamma. So if you look at this speed here, if v come closer to c, what will happen? So this is going to be equal to 1, right? Then we are going to get 0 underneath, and the gamma is going to be infinity. That means that your time is going to be infinity times t0, or you can say t0 is going to be tv divided by infinity. That means when a spacecraft reaches the speed of light, time stops. Time doesn't move. So that's one of the reasons that it's impossible to go beyond the speed of light, because even this formula will become meaningless when the speed of the spacecraft goes above the speed of light. Say for instance, if this is go above the speed of the light, then this is going to be a minus value. So we can't find a gamma when this is a minus value. And for the length contraction, he came up with the other formula, which is quite similar to what we have done now for the time, which is LV, which is the time, the contracted length is equal to 1 over gamma times L0, because do you know why? That LV is smaller than L0. So we can write here LV is smaller than L0 and TV is greater than T0. So let's look at the reference planes again. So your friend is in a moving reference plane and you are in a stationary reference plane, and your friend is a stationary observer in his reference plane, and he's looking at time t naught and the distance lv. So that is a contracted length, and you are taking a time that is dilated time. So we got the equation: the dilated time is equal to gamma time proper time. So that is, in other word, T naught is called the proper time and L naught is called the proper length. So T naught proper time is the time measured by an observer who is stationary in a moving reference plane. So he's stationary in a moving reference plane and he's measuring the time. That's a proper time. And proper length is something that can be measured by you or by him. Like, he knew that the length is actually L0 before he started the journey. So even according to you, that's L0, which is the proper length. So let's punch those numbers, that the one that we looked at before, the previous example, and assign to these variables and find out whether you and your friend were right. So you both agreed on the speed at which the spacecraft went to Mars, which is 0.866 c, which is a 0.866 times the speed of light. And the distance, according to you, it's 54 million kilometer, but he said that 27 million kilometer. And the time it took, according to you, 208 seconds, and this is 104 seconds. So let's use this formula and use these equations to justify whether you both came up with the right value. So you point the values for these v and c. So we got gamma is equal to 1 over 1 minus the velocity, the speed is equal to 0.8666 c squared divided by c squared. And if we put it in the calculator, we get 2 for this one. So gamma is 2. So now, if we look at these equations, TV is equal to gamma times TO. So TO is the time measured by your friend, which is a perfect time, which is 104 seconds, and TV is the time according to your reference plane, which is a dilated time, which is 208 seconds. And for the length, the contracted length, LV, is equal to 1 over gamma, which is going to be half time LO. So that's 54 million kilometer, and according to your friend, it's 27 million kilometer. I mean, and you can see that if you divide the length by the time, and the speed is constant, but time is changing and the length is changing. So time is not absolute. So Einstein came up with this time dilation and length contraction, and he did lots of thought experiments. So because it was difficult for him to do the experiments at relativistic speeds, but he did thought experiments, he derived this formula, and he was able to predict all these values. And after Einstein, that we still have lots of real world examples that demonstrate time dilation and length contraction. Let's look at a few examples now. So muons are subatomic particles like electrons. They are the leptons family. So they are produced when cosmic rays bombard the atmosphere, and during the collision, these muons are produced, and they have a half-life of 1.5 macroseconds, which is tiny. That means if you have got, say, 10 muons produced here, or 20, after 1.5 microseconds, you will have only 10, and then after the half-life, you have 5. So scientists, they know that based on the half-life equations that it's impossible to find muons on the surface of Earth because they will decay before they're hitting the Earth. But they observed that they are seeing lots of muons on the surface of the Earth. Why? Because they travel at the speed of 0.99 c, so which is close to the speed of light. And although for us, this in this example, this is 2,000 meters at the mountaintop, and for us that we calculate for that speed, it might take 6.5 microseconds, but for the muons, it takes only zero point 0.7 microseconds. So, which means that less than the half-life. So they are able to reach because for in their reference plane, the time is shorter, and for us, the time dilated, and for them, the length contracting. So according to the muons, they don't see a big mountain, but a little hill really. They thought that they coming from here and reaching at a shorter distance, and but the time took for them to reach is shorter. So this is a real example of that Einstein um, time dilation. And the next example is GPS. GPS is used by every one of us all the time, and the GPS systems are in the satellites. Satellites orbit the Earth at a not a very high speed, but GPS clocks that time. It always delays a bit because they are moving in relation to Earth. Because they move at a, it's not a relativistic speed, but still the clocks changes. So there are systems in satellite to change the clock back, adjust it to match the time on Earth. So that's another real example. Atomic clocks. This has been tried by several scientists to prove the time dilation. So what they did is that they put atomic clocks in aircrafts and went around the Earth, east and west in two different directions. So they measured the time from Earth, and also they measured the time when the clocks came back to Earth from with the aircraft. And what they found out is the clocks in the aircraft, they were moving slowly compared to the clocks on Earth. So that's another way that the scientists have proved that time dilation is actually real. So these are places where we're not actually moving at a very high speed, but even at a low speed, we are able to measure the effect of time dilation. So if we move in relativistic speed, as we discussed before, it's possible to notice it. Like the previous example, we can see that the time to Mars is almost halved